Okay, so let's get started, shall we? The plan is to give you a quick crash course, a little introduction to Go. I'm not sure if you got any prior programming knowledge so far, but if you got a basic understanding of programming in Python, C, C++, Java, whatever it is, you should be doing just fine here. So I'm going to give you a quick introduction. We're going to start with an obligatory hello world, I'd say, because what else are you going to do in a new programming language, right? Let's get started. I already created a little hello world Go here in Visual Code. You can use pretty much any editor you want. Bear with me maybe for a few minutes. I'll just give you a quick introduction, and then I'm going to show you how you're going to set up your environment for programming. All right, so the first code word that we're going to look at here is package, and that's pretty much how any Go file starts. You give it a name, you just declare it, what's the package name, and if it's called main, then similar to a main.c, it's going to run a function called main. That's the entry point that it's going to execute if you start a binary. And the other keyword that you're seeing here is the import keyword. This is importing another package called fmt or format, and it contains a bunch of methods that you will need to print out to a screen, and that's what we want to do. So we're calling the println method of the format package, and we're going to say hello world. Let's quickly switch to the terminal. Here's the hello world Go that we just created, and we can run that pretty much like a script like you would in Python, for example, with go run hello world.go, and it would just execute that, and it would print out hello world as we expected. What you can also do in Go, it's not an interpreted language. You can actually compile it. You can even cross-compile it. So we can also turn this into a proper binary by calling go build, and then we'll see there's a binary called crash course, and we can actually start that as well, and we'll print out hello world. I'm just quickly catching up with the chat. No, this is actually not CSH. This is actually a shell called Elvish. I can probably get into that a bit later because it's actually written in Go as well, and it's a project I'm contributing to, and I quite like it. But yeah, it's pretty much like a regular shell for all that matters now. Let's go back to the code. So yeah, as I just said, there's a compiler and there's a linking stage. Per default, Go is producing statically linked binaries. And it's a type-safe language. You got pointers, but you got no pointer arithmetics. It's garbage collected. We're going to get into that a bit later. And it excels at a couple of things. One of them is concurrency. So if you got multiple threads, if you want to do a lot of stuff in the background, calculations, rendering, whatever, Go really excels at that. We're going to get into that a bit later as well. It comes with first-class tooling. There are a bunch of projects around Go now that make really heavy use of the AST, of the compiler. And so there's a perfect tooling kit, a linter, and a bunch of other stuff that we're going to look at. It's pretty opinionated. It got strict errors. We're going to look at that. And I'd still say it's a rather simple language. And that's because I think there's in total only 27 keywords that we're going to look at. And that means you can basically start learning Go, and within a week you've pretty much covered everything. That doesn't mean you're really good at the language or you know everything, but it's not like C++, where after years of programming you're still discovering new features that you've never heard of, right? So yeah, we're gonna look at pretty much every keyword here. And let's start with some basics. For example, we could declare a new variable s, and it's of the type string, and we can give it a value. And then instead of printing out the literal here directly, we can print out the string s as well. There's a different way you can do that. You can implicitly declare s as a string, if you do it like that. Same goes for pretty much any type. So you could say, hey, I want a new integer called I with a value of 0 or with a value of 42. And you could print that out as well. Let's just run that, because why not? Hello world 42. You can concatenate strings. So you can do something like that. And of course you can do similar things with an integer again. So those are two basic types, strings, integers, obviously. We could also look at arrays, or actually called slices in Go, and there's a minor difference that we're going to discuss later. But that will be a string array or a list of strings, yeah? And you could give it some values. Oh, forgot the quotes here. And we could also print that out. Let's look at that. Hello world, and the format println, and because it's a slice, actually adds those brackets around here. You could also add stuff to this array, to this list. For example, like that. And that's using the append method. And what it does here is you give it two parameters, the original list and whatever you want to append to it, and it returns a new list. And we're just going to override SL with the new content here. We could also do it like that. And assign this appended value to a new list called sNew. That wouldn't change the original list called SL here. That would remain with the original value of hello. And we can access the index of such an array, for example, like that. That would only print out hello in that case. You could also do it like that. You can give it a range, and then it will print out both values again. No, it actually doesn't, sorry. Like that. And you can also say start from 1 and then until the end. All right. So those are some basics. I just mentioned that Go comes with a pretty strict error system. That actually means if I declare a variable and then I'm never going to use it, the Go is actually going to complain and not run that. Let's have a look at that. Here it complains, X declared and not used. So let's actually use X again. In whatever way that will be, right? And it's happy with that again. And that, at first, you're really confused by that because that produces a bunch of errors. Where you're not used to seeing errors, especially when you're like refactoring code and you're moving stuff around, and suddenly you end up with unused variables and the code won't run anymore. But in the long run, you'll realize this is actually a great feature because it prevents you from collecting up unused variables that no one knows. Are they still used? Are they actually doing anything? And the compiler won't tell you about it. Obviously, in other languages, you get warnings, so you'd have to look at those warnings. But in Go, it actually treats unused variables as strict errors already. So, like in other languages, we're going to look at loops. And in Go, there's actually only one kind of loop, even though you can do pretty much with it. So let's say we declare a new integer I with a value of 0. And we're going to execute the loop as long as I is smaller than 4, and we're going to increment I. with every turn, with every iteration. And let's just print that out again. So this is probably a pretty standard for loop as you've seen in other languages. We can just run that. And it would iterate 4 times. But you can also do it in the style of a while loop. So let's say we're going to declare I as 0, and we want to execute a loop as long as I, or while I is smaller than 3. Let's try that again. Actually, we should do something here. We should increment I, otherwise this will loop forever. And we're going to run it again, and we can see 3 iterations. And then we can also range over things. So this is probably called a for each loop in other languages that you might know. Let's say we got the slice of strings again. Hello world here. And we want to loop over those values inside the array, right? So let's do that. And let's use printf. You've probably seen it in other languages as well. And it got a pretty similar syntax as in C, for example. So what we do here is we declare an array with 2 values, hello and world. We're going to range over that list. And for every iteration, we're getting 2 values declared, I and S. I is the current iteration number. So it starts with 0, and then it goes to 1, 2, 3, and so on. And S is the current value. So this would mean in the first iteration, we will get I equals 0 and S equals hello, because that's the first item in the list. And in the second iteration, I will be 1 and S will be world. Let's just try that. And as we expected. So I'm just going to quickly catch up with the chat. Yeah, Go does use a lot less punctuation. I should actually go into that. You can actually write something like, yeah, and here's the semicolon. But the semicolon, pretty early in the language definition, around 10 years ago, they actually decided to get rid of semicolons altogether. And that also means that you have the strict rule of only one operation per line. You can't do, in C or C++, you could do stuff like that in a single line. And that's not actually allowed in Go. It also lacks the brackets, yes. So if you look at the for here, in other languages, this would probably look something like, like that, and so on, right? It lacks those brackets as well. This also means if you'd write something like, something like that. And again, here the brackets are actually missing. You can use them, it doesn't complain about that. And you can also do stuff like, yeah, you can do that. So we can try that. And actually it's lying at that point. No, it's correct. All right. Let's move on. Maybe we'll take a quick look at maps now. Oh, sorry. I should finish catching up with the chat quickly, because there's a bunch of messages. Yeah, so again, the shell is actually called Elvish. It's a shell written in Go. It's a pretty interesting project. The theme that you're seeing here is certainly inspired by Powerline. It's actually something that I've written myself. It's an Elvish module. You can find it on GitHub if you're interested. Just go check out my GitHub profile. It's on github.com/muesli. That's MUESLI. All right. So yeah, let's take a quick look at maps. We can declare a map and reserve some memory for it by doing this here. This is just an example. Here we have a map with a type, with a key type string and the value type integer. And you can already see Visual Code here is already complaining because I declared m and I'm not actually using it. So let's use it. And just like that, you can actually assign values in a map. So the key with the name foo got a value of 1337, and the key with the name bar got a value of 42. And we can access them and print them out, just like you would expect, probably like that. You can also range over maps, just like we ranged over lists. So let's try that. You would do something like that here. And then for every iteration, you would have the key and the value set. Let's quickly print that out, maybe. And you can also check, I mean, actually, let's quickly run that, just so you can see what it does. Pretty much what we expected, I guess. But you can also check if a value if key is already in a map. So you can do stuff like that. And in that case, value would be 0 because that's the default value for an integer, but OK would be false because we didn't find the key unknown in the map. If we do it like that, if we'd access the key foo, then the value would be 1337 and OK would be true. And let's try that out. Perfect. No, there's no shorthand like that, like you might find in other languages. This notification is this notation is strictly for accessing members of structs. We're gonna get to that in a second. All right, and let's look at the method maybe. Out of the main, we're gonna write our own little method. And we're just gonna call it simple. It expects one parameter. Again, what you would notice here is that the order is different than it is in other languages. Usually you would write something like the type first and then the name. And in Go, it's the name first because that's considered more important, and then the type. And then it has a return value, for example, a boolean. And we can return, so let's actually call this method something like is positive, and it would return if I is greater than 0. And you, just like in, I think, Python, for example, but unlike C or C++, you can actually have multiple return values as well. So let's try a different method, call it work. Again, it expects an integer. And it actually returns an integer, and it returns a bool as well. And let's just increment I by 1 and just return always true. It doesn't make any sense, but yeah. And we could call that, for example, like that. Let's use OK as well. Print out those two values. So we would expect to get this number incremented by 1, and true as the second return value. Let's print it out. Yep. You can also declare functions just in line. So similar to the function that we just had, let's declare a function right here inside main and return I plus 1. Yeah, that's the incrementer function. Let's print that out. We can directly call it here. We gave it a name, and we can pass it a value as it expects and print that out. And again, 1,337. So, but let's make this a bit more fun even. A function is a first-class value in Go. This actually means you can, just like we declared here, a function in line, you can actually use functions and use them as return values, or we can expect a function as a parameter. So let's do a method called pigmath, and it picks a mathematic algorithm or something depending on the value that it passes in, and it returns that algorithm as a function. So here, this func int, the entire part that I selected here, this is actually our return value, yeah? And this return value, this function, is expected to be returned by pigmath when we call it. So let's do that again once more. We're gonna declare another method called increment again. And it just returns I plus 1. And now here in pigmath, we can say, I don't know, if I equals 1, then return the increment function. Otherwise, return some other method, for example, a square root method. Yeah. So that would mean we can call this method now, pigmath, and we pass it a 1. And we expect it to return the increment method here. So let's store that method that it returns, that function that it returns, as f1. And let's call pigmath again with a value of 2. And we expect it to return the square function. Let's try that. So f1 is the increment method. That's what we expect to be get returned. And we can call that with 1336. And we expect it to return again 1,337. And there's the other method called f2, and we can call that as well. And we're just going to call it with 4. And we expect that to return this to be the square method. And hence we're going to call sq here with a value of 4. So 4 times 4, 16. Let's run that. Actually, I should save it before I try to run that. Here we go. Yeah, so dialog a lot. Yeah, certainly there are some, Go clearly has some predecessors, and it's borrowed from a lot of other languages. So certainly there are similarities to C, to Python, there are similarities to Lua, but also to Java and C#. We'll get to that in a minute maybe. Let's take a quick look at Variadics. Let's declare another slice of strings. Again, our hello world slice. And we can declare a method. We'll call it printer here. and it expects an undefined amount of strings. That's what ... string declares. So 0 or many strings, we don't know. But inside here in this method, we can again treat it as a slice and range over it and print out every single one. And now we can call this printer, and we could do it like that. And so on, yeah. Let's quickly do it like that, just call it like that. And it would receive both those strings as an array, and it would iterate over them and print out hello world. But there's another thing that we can do, and that's the slice array here. We can use it in the other direction, sl ... That means expand the string slice into single values that it will then pass on as a parameter to this method printer. So essentially what it does here is, if I write it like that, it will do and so on for all the values of SL. So those are the two ways to work with variadics. You can receive them as an array, an undefined amount of strings or of integers or whatever it is, an undefined amount of functions if you want to. And the other way is we can expand a slice just like that with ... Let's take a look at structs. You've probably seen structs in other languages as well. We can, for example, declare our own type circle. And it's a struct. That means it contains other members, other values inside it. And obviously a struct got a radius, right? And we could imagine that we have another type, a rectangular, and it got a width and a height. Or we got a cuboid. And the cuboid actually has certain properties that the rect has as well, namely a width and a height. So we want to embed that rectangular inside the cuboid. And we're going to extend it by another value, the length. Yeah? So embedding another struct inside a struct is essentially as if you would write it like that. But you don't have to. And if I'd extend this here by, say, a name, then suddenly we would also have inside this cuboid a width, height, and a name. Quick question from the chat. Which data types do exist by default? We can quickly go through them. You've probably heard of all of them. There's a Boolean, there's a string, there's an integer and an unsigned integer in various sizes. There are floats and complex values. There are maps and there are channels. Channels we're going to get to in a bit. And I think those are all the default data types. All right, let's get rid of the name again because it makes no sense. Yeah, for complex is for complex numbers. And let's just declare our main method again. And let's instantiate such a circle, for example. You could write C as a circle with a radius of 5. Just like we could declare R as a rectangular with a certain width and a certain height. Or the cuboid. And here we could declare it like that. We could pass in the existing rect R to initialize cuboid with a width and height as defined here in this line. Yes, if you embed a struct into another struct, you can access the members directly. We'll get to that in a second, actually. because let's quickly finish this bigger picture here. There's something else you can do with those structs, and that is, let's imagine you get a method and you wanna calculate the area of a circle. Yeah, let's call this method area, and let's say it expects one parameter, a circle, and it returns a float, the size of the area. And I hope my math isn't playing any tricks on me, but that would essentially mean like that. I hope that's right. It looks right to me. And we could call the method, obviously, and call area. And actually now we need a circle here. We're gonna pass C, the circle, to it, and we're gonna print out the size of the area. Let's quickly try that. And there's the size. But you'll quickly notice the rect will have an area size as well, and the cuboid, so does the cuboid, right? And at that point it gets a bit nasty, because then you're going to write area circle and area rect and area cuboid, when you can actually do something much nicer. And that's, instead of passing C, the circle here, as the first parameter, we're going to actually attach an area method to a struct, to a type. So we can write it like that. It doesn't change anything here in the definition of this function, but it changes something down here. Now we can call area as a method of C. Just like that. And we'd get the same result, obviously. And similarly to that, you could imagine an area method for the rect, for the rectangular. And that's the width times the height. And we could print that as well, obviously. Here we go. And just for good measure, right? Let's also define an area method for the cuboid. And now it's getting a bit more complicated. The width times the height. So we're directly accessing the width and the height of the cuboid, even though it's part of the embedded rectangular struct. Plus the width times the length, and the height times the length. I think that should do it. And let's print that out. Here we go. So I'm quickly looking at the chat again, if there are any questions. Yeah, okay, pretty much caught up with it. So, now, there's something that you probably might become aware of here. I've also mentioned it. We got three different, we got a circle, we got a rectangular, we got a cuboid, so essentially geometric figures. And they all got an area. That's the one thing they got in common. Now, there's actually something we can do. We can say, we declare a new type called shape, geometric shapes. And we say anything that has an area method that returns a float 64 is something we consider a shape. That's the one thing they all got in common. And now, let's do something funny. Let's have a measure and print method here that expects a shape. Any object of the type shape. And we're actually going to do two things here, I think. We're going to print out the type of the shape and its actual value. And since we said shapes have a method called area that returns a float 64, we can also call this method area on a shape. So now, how do you define those interface types? The funny thing is, you don't do that. It's implicit. Anything that has a method area that returns a float 64 is considered a shape. So even though we got a circle, a rect, and a cuboid here, we can actually pass them as valid shapes to measure and print. So let's do that for all of those 3 here. And let's run that. And we see, first we passed in the circle. It tells us in the printf here, the person t prints out the actual underlying type of the value that it passed in. And it tells us, yeah, this is defined in main circle, in main as a circle, sorry, with a radius of 5. And then we're calling the area method of the circle. So here for the C, yeah, it's actually gonna call this area method because that's the area method that belongs to circle. And for the rect, it's gonna call this method here because that's the area method that's attached to the rect. In other languages, like in C++, for example, you would have, for every type, you would have to say and tell the compiler, hey, by the way, a circle actually inherits from a shape. Yeah, it's a shape. We can use that as a shape. In Go, you don't have to do that. It's implicit. Yeah, Kuros, exactly. That's how you approach OO programming in Go. And it makes it super handy because even though you're, for example, you're depending on different packages that don't know about your types, you can still use them with your types because the inheritance is implicit. It doesn't need to know about it. It automatically fulfills those types, those interfaces. All right. And now that I just mentioned that, actually, we should take a quick look at maybe two of the most common interfaces you'll get to work with in Go. And that's the IO reader and IO writer interface. And they look like that. I'm just gonna quickly write it down here because they're so short. It can't harm. Let me get that right. Actually, let's keep it simple. That's the reader interface. So anything, any type that provides a method called read that can read to a slice of bytes, basically a binary blob, yeah, and return an integer and an error, is implicitly of the type reader. And the same goes for the type writer. Writer is also an interface. And any type that has a method called write that expects, again, a byte array, and again returns how many bytes it has written, and if any error occurred, is implicitly of this type writer. And that makes it really easy to pipe together stuff like you're downloading from a network socket and it provides you such a read interface, and you can just pass it on to any writer. Say you want to write to a tar file or a gzipped file, or you want to pass it on to another network socket. You can just pipe those two types together with those interfaces, even though they don't know about each other. There's no inheritance, no explicit inheritance going on. All right. Let's move on with something a bit more simple, but just as fascinating. And that's imports. So you've noticed what we did before is we imported the FMT package or the math package. If you want to import multiple packages, you can also run it like that. Yeah. But you can also do something pretty cool, and that's you can actually import packages from GitHub or GitLab or other sources, as long as they're part of a Git repository or a Mercury repository. There are other source control mechanisms that are supported in Go as well. I'm gonna focus on Git here. And let's import the package. That's the package that I've written myself. It's called Cache2Go. It's a little caching library. And we can directly use it. We can call a method inside this package. And we're going to create a new cache called myCache. And we could add a new value to this cache, and we can tell it to only live there for a couple of seconds and then time out and get deleted automatically. So I think I don't have that on my system just now. If I try to build, it will actually tell me, okay, I can't find this package. But this is where the build metadata, the build information, and the source code intertwines in Go. In other languages, you might have that separated. Yeah, you define the dependencies somewhere else, not directly in the source code. So in C++, it's pretty common. You have your actual project, your source code, and then the build system is a bit separate from that, where you actually define all your dependencies, all the libraries you're looking for, stuff like that. What we can do in Go here now is we can actually call go get, and it will analyze our source code and try to resolve all the dependencies that we need to compile this code. So we can call go get -v simply verbose, so it'll tell us what it's actually doing in the background. And you can see that it downloaded and installed this Cache2Go library for us. And now we can actually build the code. So I'm quickly going to catch up with the chat again. Yeah, so importing directly from web sources sounds questionable to Zordai a lot. Understandable, that was my first reaction actually as well. But in reality, it turned out to be a huge lifesaver. It makes it so much easier to actually deploy and to manage the build system and not keep it as a separate thing that's living outside of the source code. This also means it makes it a lot easier for all the tools, the linters and stuff like that to really work within the scope of your project and all its dependencies. And then there's stuff like rendering and modules that we're gonna get to probably in another tutorial, where you can actually really define which versions of a dependency you depend on. So you're not gonna always depend on Git master, but you can say, I want a 1.x release or the 2.x release, stuff like that. All right, quick detour to the imports. Let's look at another cool code word. That's the defer method. Clean up our code a bit here. Let's imagine we get a cleanup method here called cleanup. And it's not going to do much. It's just going to print out cleaning up. In reality, we'll probably do stuff, close the database connection or stuff like that. And that's a pretty common thing. You would do your work here, and then at some point you want to exit your program and you're going to call the cleanup method. What you can do in Go, actually let's define a work method here as well. Yeah. So if we call that, we would call the work method first, it would print out working, then we would call the cleanup method and print cleaning up. right? Right. But often you end up forgetting stuff like that. You often end up in situations where you need to make sure that you close a file handle when you're done with it, for example, or a network socket when you're done with it. And hence, there's a keyword in Go called defer. And we can do stuff like that, defer cleanup. And that will make sure that cleanup gets called whenever we're done with the main method. So even though we wrote this code in this order, cleanup won't get called directly. It first executes work, and when work is done and main shuts down, finishes, then it will actually call cleanup. And so we actually end up with the same order here in the output. And this is pretty handy. This is super handy, as I just mentioned, for taking care of file handles that you need to eventually close, database connections that you need to eventually close, stuff like that. Let's take a quick look at concurrency. As I've mentioned pretty early on in this video, in the stream, Go excels at concurrency in many ways that other programming languages don't do. I don't know if you've got any experience with threading in C or C++, and if you do, you probably can tell some stories, right? It can be a pretty painful experience, and Go tries to streamline that. Let's take a quick look at it. Say we got a work method, yeah? And it expects a parameter I, type integer again. Let's quickly print that out. Working I. And then inside this method, we're going to do some really heavy work, right? And we're going to simulate that by sleeping here. But in reality, we would do something crazy intensive, CPU intensive, for example. We would render some stuff, or I don't know what we do. And we're just going to print out when we're done with it as well, so we know. And now we can call this method, right? We give it, let's give it a value of 3, so it's actually going to sleep for about 3 seconds, printing out working before and work done afterwards. Yeah, it did crazy intensive stuff, as we can tell. So, but we actually want to move on with our life here in the code, and we want to do other things in the background while we're waiting for the network, while we're rendering, while we're doing busy stuff. What we can do in Go is we can call a method, and we append it with Go as a keyword. And what's happening now is that this method work3 will be started in the background. It's, I don't know, if you know Bash, you've certainly seen it. You're starting a program like foobar with the ampersand in the end. And then it's going to fork to the background, and you're back in the terminal and you can keep working, but this program will run in the background. That's pretty much what Go does here, if you use this keyword on a function. It will launch this work3 in the background, and you'll continue with your life here. Trick question, what's going to happen if we actually run this now? Let's try it. It only prints out hello there. There's no working, there's no work done. What's going on here? So imagine work gets scheduled to be run in the background. It's not going to start at this very moment. It's scheduled to run in the background. It's first launching maybe another thread. It's going to do that in the background for you. And then it's actually going to call work. But we're so quick, we're just printing out hello there, and then main ends. And when main ends, the program ends. So the scheduler actually never got to the point where it managed to start work. But we can give it some time. We can sleep here for 5 seconds, right? Just to make sure, if we are sleeping here for 5 seconds, then certainly the scheduler would have had enough time to launch work for us in the background, and we should see some more. And certainly so we do. Hello there starts up. We're working here for 3 seconds. We're done with the work, and after 5 seconds, the program shuts down again. Okay, let's make this a bit more interesting. Let's do it like that. We're declaring a for loop. We're going to run it a bunch of times. And in every iteration of this for loop, we're going to call work with the current value of I. Let's try that. So it's going to start up here. It's spawning 4 work methods as we'd expect. And you will actually see it came here, and in the first iteration it called work with a value of 1. And it scheduled that in the background. And so then it goes there and schedules work with the value of 2, 3, and 4. But they're not guaranteed to start up in that very order. It depends how busy your CPU cores are, for example. But it will launch them eventually, right? And we can see, yep, the method work that we call with a value of 1 finishes first because it only sleeps 1 second. With a value of 2, it sleeps 2 seconds, and so on. So they actually return in the correct order as expected. Quickly gonna catch up with the chat. Sir Dial-Out-A-Lot writes, weird that it just quits. Not really. That's pretty common in pretty much any programming language. If you're at the end of the main method, it's gonna actually actively quit your program. Even though there's maybe stuff scheduled in the background, even when there are threads running in the background, they're just gonna get terminated at that point. And Fnord writes, can background methods return stuff? Yes, they can return stuff. Not in a traditional way as a return value, but we're going to get to that in a second. There's a concept and a type in Go called channels, and you're going to use that to communicate with stuff, with methods running in the background. And yes, Sir Dial-Out-A-Lot, there's a way to wait for those background functions to come back to you. We're going to look at that as well. Let's clean that up maybe. Actually, let's take a look at channels, because that's how you communicate with threads with concurrent methods in the background, concurrently running methods in the background. So we can declare a new channel. We use the make method because it allocates memory actually in the background for that. And we declare a channel of the type string. It could also be a channel of the type integer or any other data type, even self-declared data types. But for now, let's say that there's a channel and this channel transports strings. And we can send stuff to this channel like that. Now we're sending hello world down this channel. And as you can imagine, there's a sender and there's a receiver. On the other end, in some work method, for example, we could read from a channel, and we could do that like this. So here we declare whatever comes out of C, right? It even points in that direction, gets declared as S. So S will be a string here, because that's what comes out of a string channel. And C, we can pipe something into that channel like that. Again, here we need to have a string because it's a string channel. And again, yes, those channels can handle custom data types that you declared yourself. We're gonna get to that maybe in a second as well. So let's write a quick example that uses channels. For now, we're just gonna declare C as a global variable here. It doesn't need to be, but for the simplicity, we're just gonna do that now. And let's have a method, a function called pinger. And the only thing that pinger is gonna do, it's constantly gonna send a ping down the channel, then waits a second, and then it would forever and ever and ever continue to send a ping once a second. And let's have another method called printer. And that's also going to run forever. And it's trying to get a new message out of the channel, a new string out of this channel. And we're going to declare it as message, MSG. And we're going to print it out whenever we got it. And now we're going to run ping on the background. And we're going to run the printer in the background as well. And we're going to terminate the application after 5 seconds. We're going to sleep for that long. So for 5 seconds, pinger will run in the background. Once a second, it's going to send ping down this channel C. And the entire time, printer is going to run. And it's trying to receive a new string out of this channel and print it out. Let's do that. Are you surprised? I'm not sure if you are. No, probably not. That's exactly what we expected, right? We got two methods running in the background. One is sending a ping once a second. The other one's just sitting there waiting for a new message to come down this channel and print it out. And what you may have noticed at that point is this line here, line 19. It's gonna block and wait until there's a new value coming from the channel. It's going to wait here. It's going to sit and wait here. If there's nothing coming through this channel, it's going to wait here forever. But once it got a value, it's going to continue, and then we're going to wait for the next value. From the chat, how long have you worked with Go? I probably started in 2011 or 2012. I was pretty early. So the language, I think they started development in 2009, and the earliest releases were in 2010 maybe. And pretty soon after that, I got intrigued by it and by a bunch of its concepts, and mostly its simplicity, really. Other than that, I got programming experience in C++ and C and Java and a lot of other languages for, oh gosh, for almost, well, for almost 30 years now. Yeah. Okay. Let's extend this example a bit, maybe. So as I said, this was a bit dirty. We declared this global variable there. Let's make a new channel inside the main method here. And this is a channel that we're going to use to send integers over. And we're going to call a method Fibonacci. And we're going to pass this channel as a variable to it. And we'll have two worker methods. One printer, and we'll make a second printer. And we both pass channel C to it. And then again, we're going to keep this program running for 5 seconds. Let's actually declare those methods. Fibonacci. It expects an integer channel. And in there, we're going to do the typical Fibonacci stuff. So I'm going to explain those lines in a second. And we'll have, actually, a typo up there. And we have a printer method. It gets an ID as an integer, and it also expects this channel of type integer. And again, we're going to print out whatever we get. First, its ID maybe, and then whatever value it got. And we can write it like that as well. And we're going to sleep here for a second. So what is this going to do? It's going to start up the Fibonacci method in the background. It'll start by writing X to the channel. We declare two things here. X and Y are 0 and 1. This is the same as if I'd write. Yeah? You can do it like that as well. And then we're going to write X to the channel, because that's our first Fibonacci value. We're going to start with a 0. And then we're going to redeclare X and Y. We're going to pre-generate them for the next iteration. And here X becomes the current value of Y. That would be a 1. And the new Y is X plus Y, typical Fibonacci. And then we're just going to print out that we pre-generated the next number X. And the printer here, we're actually going to launch that twice in the background. One printer got the ID 1, and the second one got the ID 2, obviously. And they both get this channel C. And they're going to, forever and ever, they're going to loop infinitely and print out whatever the value they're retrieving out of this channel. And again, this here is just reading out of the channel. I could do it like that as well, right? Maybe that's a little less confusing for you to begin with. And then we're gonna wait a second. Maybe it got to do some work again with this value that it retrieved from the Fibonacci generator. Let's try that. Let's run that. So what do you see here? The first value that the Fibonacci method writes to the channel is 0, and printer 1 gets that. And then it generates another number and another number. And those actually both end up with printer 2. So it's not defined who's gonna end up reading from this channel first. Whichever printer is ready gets the next value and is gonna do some work with it. So you can have multiple workers reading from the same channel, and you can launch, say, 8 worker threads in the background, and you're just waiting to be fed with another value coming down from a channel, from a generator, or from a network source or something, or from the database, something like that. And that's pretty handy. Something like that in C, C++ is a lot of work, and you're gonna get it wrong a lot of times. There's so much concurrency that you'll end up accessing the same memory blocks twice at the same time, and you're gonna run into erase conditions, stuff like that. Okay, I'm just gonna catch up with the chat once more. Yeah, essentially this is first in, first out, correct? Yeah. Can errors occur when we pipe from into the channel? Yes. So there's one situation, if you're trying to read from a channel that's closed, and we're actually going to get to that in a second, you can close a channel, and by closing it, you can tell anyone who's reading from a channel, hey, I'm done with my work, I'm going to close it, don't expect any more values. And once it's closed, you can't actually write to it anymore. That would lead to a panic. And you can also check if a channel is closed or if it's still open. You can do stuff like that. So let's use this channel concept, and we're gonna look at, sorry, just one more question coming in on the channel. How is the channel capacity limited? Yes, in this case, in the default here that I just showed, this would actually be an unbuffered channel. You could write to it and write to it. But as long as if you use this channel and you try to write to it, and there's already something still in this channel waiting to be read on the other side, this call is actually gonna block and wait. And this is actually pretty handy because this means if you're generating a lot of stuff, you don't want to go on generating stuff forever. You actually want to wait for the worker threads to become ready for someone else to pick up new work. Yeah. Craft AMAP asks, is there a method to get all elements queued in a channel? Well, you could just simply keep reading from it. You can even range over a channel. So if I got this channel, I'm just gonna quickly change this here. You could do something like you could range over this channel, and then you would keep reading data from it until it closes. And so you could run it dry and just read all the values and store them in a slice or something like that. So that's the way how you could just get all queued elements from a channel right now. So basically what I was just getting to here is a bit of a flow control where you can control how the data is running through your program. And let's actually take a closer look at that, maybe. Let's say we got a work method, and it's a bit of a silly work method actually. It's just gonna return an error whenever you call it, because whatever it does, it apparently fails. And let's say there's a download method, and we're gonna pass a so-called context type to this download method. We're gonna get to that in a second. And in this download method, yep, we want to download something from the interwebs. So let's do a new HTTP request of type GET, and God knows, can't come up with a better example right now. We're gonna get the homepage from Google. And we're just gonna use the default settings for the HTTP client. That's the HTTP default client, and we're gonna do this request. We're gonna execute it in this context that we passed in. If there's an error and we couldn't get that page, we're gonna abort and return. Otherwise, we're just gonna print out the status code that we got from this request. And then there's a think method. And this think method also operates in a context. And here we're gonna learn something new. And that's the select keyword. And in a select, we got two cases. The first case is when we read something from a channel that the time.after method provides. And this time.after is a function that returns a channel to us. And it will essentially wait for 2 seconds here, if you call it like that, and then it will close the channel that it provided to us. So we can say here, that's the first case. When we read something from time after, and we're just gonna print out, oh yeah, we're done thinking now. And the second case is gonna be if the context is done. That's a method the context provides us. We're gonna abort thinking more. Contrived example, I'm sorry, can't come up with anything better than that right now. Again, catching up with the chat quickly, you don't even need to import anything for HTTP. Actually, I do. I'm sorry. What happens here is that the Go tools will automatically detect that I need a package called HTTP and I didn't import it. So it will guess the right package here, and that's net/HTTP, and import that for us automatically. So if I remove that here and I press save here in my editor again, and will actually re-add that for us because that's how I set up Visual Code. You can do the same thing in Vim, in any other editor, because this isn't a feature of Visual Code, really. This is something that the Go tools provide you. They will analyze your source code as the compiler would, analyze the syntax tree, figure out any errors, and they actually are able to correct them for you. So I don't use that too much, but for imports I actually do it because it saves me from typing this import over and over again. Okay, and let's actually declare a main method where we combine those pieces here. So we declare a new context with a cancel method. And we're just going to launch that in the default scope of the program that's called context background. And then we're going to launch a new method, a new function in the background. And that's going to call work. And if work returns an error other than null, so any error essentially, then we're going to print out that the worker failed, and we're canceling all other operations. And we're doing that by calling cancel. Cancel here is provided to us by context with cancel, and it returns a method to us. Remember, functions in Go are first class types. So we can just call cancel here. And we're just going to launch this function that we declared inline here directly. So this will be the same as if I take this function here. Oops, sorry. And I'll give it a name, foobar. That's the stupidest name. So I call foobar in the background, right? And it's just going to execute that. That's the same as declaring it inline. I'm just going to inline declare a new function. It doesn't need a name. And we're just going to call it directly without any values. And then also in the background, we're going to start the download operation and the so-called thinking operation. And again, because everything's running in the background here, we're going to give it a little time to execute. So what's happening here? We're declaring a new context. With this context, we can actually control the flow of the download and the think method. They both get passed in the same context. They're both going to operate on the same context. And the think method, after 2 seconds, it'll reach time after, and it prints out done thinking, and it's gonna return this method. It's done with this method. Unless context done gets called first. At that point, it goes, oh, okay, the context is done. I need to abort thinking. Something else happened in the background. And this is pieced together here with this download method that tries to get the home page from Google. And it's gonna execute that in the same context. And if there's an error, it's gonna abort downloading. And let's see how that works out if we're gonna call it. Can you see what happens here? Remember, there's this work function. This work function, if it returns any error, we will cancel all operations. Because apparently we don't need the data, the homepage of Google anymore. We don't need to download this anymore. And we don't need to think anymore. We can abort that because work failed and we don't need those values anymore. But let's say work doesn't fail. Work actually succeeds and we need those values. We need to download this homepage because we need to do some stuff with this data here. Let's call that again. And work didn't fail. So we executed the HTTP request and we kept on thinking. So Dialog mentioned this is pretty confusing. I'm sorry, yeah, flow control is confusing. How can I do a better job of explaining this here? So essentially we want to run 2 things, or it's actually just start with 1 thing. Maybe that makes it a little less confusing. We're only gonna launch the download method in the background. We can actually do that first. Maybe that makes a bit more sense from a flow point of view. So we're gonna start a download. We know we're gonna want to do some stuff, and we need to download some stuff from the interwebs. In this case, it's a silly example of downloading the Google homepage, but maybe we want to scrape some data from it. And this work method here, this could be a new HTTP connection, incoming HTTP connection to us, or this could be some database operation or something like that. But the work and the download methods are intertwined. They're connected to each other. Either both work, or we can abort. If one doesn't work, we can abort the other. Let's say it like that. So we're gonna start the download method, and we're gonna give it some time. It's gonna do its network request in the background, and it's trying to download this homepage from Google. And in the meantime, we're also gonna start calling work. But then there's a problem, and work actually fails. For example, it can't connect to the database. And then we realize, oh, we actually don't need to finish this download, this network request here anymore. Because maybe we're downloading a gigabyte of data here, yeah? But we don't actually need this data anymore because we can't connect to the database. At that point, we can call cancel. And this cancel is connected to this context that we declared here. See, both this context and cancel are created by the same context with cancel method. And we're gonna pass this context on to the default client to this network request. And because we cancel it now, the HTTP client will actually get the information, hey, you've been canceled, your context has been canceled, please abort. And it will actually immediately abort return with an error. And that's how you can control the workflow. You don't have to download the entire gigabyte of data if you already know you're not going to need it in the end. If you already know the incoming HTTP connection has died and whatever work you've been given is actually not needed anymore. Exactly. This cancel is not a generic one. It's connected to this context. Yeah. And you could call it, or we call this work context, and we call it work cancel, yeah. And then obviously you would pass on work context here, and you would call work cancel here. So this is not a generic name. This is something that we just defined here. All right, I hope that made it a little clearer to you how it all works together. And obviously, I tried to start this example here with 3 parallel running jobs, because in reality, usually you're gonna launch a bunch of worker threads, and you're gonna wait for all of them, and then one of them fails, and you have to abort all those other worker threads. Yeah, those contexts are pretty amazing, and you will see that you can usually use them in context with anything that you typically launch in the background, like a database request. They got contexts. The HTTP requests got contexts. And maybe your own stuff got context, and you're gonna abort it if you don't need it anymore. Okay, let's get back to some more real-world stuff maybe before we're gonna finish up for today. What you'll do a lot probably nowadays is JSON encoding and decoding. So I feel like I should give you a simple example how you can decode some JSON that you retrieved online. So let's say maybe we'll do a request. We'll do a simple one. We don't need context or anything here, so we can just call HTTP GET. We're gonna get something from I think it's called IP API com/JSON. So what it actually returns is your own IP address and stuff like your geolocation information, stuff like that. And we're going to use the defer method that I showed you before, and we're going to tell it this HTTP request returns a new body, which is a reader, and we will have to close this. This is a network operation. We have to tell it once it's finished, when it can close its sockets and stuff like that. So we're gonna tell it, hey, whenever this main method finishes, make sure to call response body close, so we can't forget it later on. And that's pretty handy because those two lines are right next to each other. Yeah, it's not like the close is it's 30 lines down the code after a bunch of for loops and whatever, and eventually you're just gonna forget it, and you don't know how it's related to opening anymore. Usually you open and then you write defer close right after that. And this will give us a JSON response. We're just gonna call the JSON response, and we declare that as our own type. It's a struct that has a bunch of members, like the country, the city they're returning, I think, and even the ISP they're guessing that you're using. And yeah, we just gonna declare J as our own struct JSON response, and then we're gonna decode into that. So we got a JSON decoder that expects a reader where it can read from, and that's the response body. It could also be a file on our disk, for example. Remember, those interfaces are pretty handy. It doesn't really depend on knowing if this stuff comes from HTTP, if it comes from FTP or your local disk. You're just gonna pass it a reader, and since this returned request got a read method, it will fit this interface, and we can use it with a JSON decoder. And we're gonna decode it into J. And here I'm passing it the address of J in memory, so it can actually override data in our JSON response here. And then we're just gonna print out whatever we returned. Like that maybe. So we're gonna print out the city, the country, and the ISP it guessed. All right, let's call that. Hello, Stockholm and Sweden. You're connected via Portline network. I'm not actually in Sweden right now. I'm not just using a VPN here, so it thinks I'm from Stockholm, Sweden. So again, what is it doing here? It creates a new HTTP request. This returns a response and actually an error, and I ignored the error here. You can do that with the underscore. And then I'm gonna tell it, okay, whenever we're done with this main method, actually make sure to close the network sockets. Then we declare J as our JSON response. It contains 3 members, country, city, and ISP. And we're gonna start a new JSON decoder that's reading from the responses body and decodes into J. And we're just gonna access the members of J and print them out. And that's 5 lines of code here, and you essentially did an entire HTTP request, you decoded JSON, and you printed it out even. So let's look at the other side of things. I don't know how many of you are writing little microservices nowadays, basically where you end up writing a little process that's like a web server, a RESTful API in itself. Sorry, I'm just stopping here for a second because there's something coming in the chat. How do you handle errors in the decoded data? So this decoder that we just used here, it actually would return and give us an error. Here, this the decode method returns an error. So if the decoding failed for whatever reason, I could just get an error here, and I could check for the error. I could print it out, do whatever with it. If city didn't exist in a response, that's another question coming in on the chat, then it would contain, city would be empty, would contain a default value. Sorry, let's look at that again. So the default value of a string is obviously an empty string. So city would just be an empty string. I hope I understood that question correctly. So yeah, let's take a look at the other side of things. If you're writing your own little microservice, your RESTful JSON API, stuff like that, you usually end up connecting your own little program with Apache or Nginx, stuff like that. But you could also write your own little web server, your own little Apache in Go if you wanted to. And that's actually, that sounds like a terrible idea. but it's actually pretty useful and not that complicated. So let's get rid of all that for now. There's an HTTP handle func method, and we tell it, hey, you operate on the root path of our web server here, for our own little web server. And any incoming requests, you're going to call a method that we're going to declare in a second here called handler. So let's declare that method, our handler method. There's an HTTP response writer, and there's an HTTP request that we expect as parameters. And whenever we call, first of all, we're going to print out that we're busy serving a request right now. And then we're going to write to that writer with the fprintf method. You've probably seen it in other languages before. And we're just going to return some silly hello. Now in the main method, we're just going to print out that we're starting listening on HTTP port 8123, whatever. I just made that up now. And now we actually need to start that web server as well. Listen and serve. We're going to tell it to listen on all local addresses. You could also specify a specific IP address here, but on port, 8123 we said. And we don't give it a separate handler because we already declared the handle func here. So this starts up our own little web server. Listens on port 8123. Whenever there's a new request incoming, it will actually call the handler method, and it will serve this request, and it will print out, hi there, I got love for you. Let's try that. So we're going to start up the web server here. We're going to listen. Let's open up a new terminal and increase the font a bit maybe. So, and let's just use curl to try and get something from it. And indeed it returns, hi there, I got love for you. And we'll see in the other terminal that it actually received the requests and started serving. So this is your own little web server in about 18 lines of code, not even 17. This is actually going to execute all incoming requests in a multi-threaded fashion. It's going to call those handler methods in the background for you. We could run a little worker benchmark or something right now if we feel like it, and you'd achieve like crazy amounts of requests per second. You could serve with that. And let's actually get a bit more serious, because nowadays you need TLS certificates, right? We could really do that, and it's not hard. I'm just going to show that because it's funny how easy it is for now. So we're going to use AutoCert. We get our own certificates. Let's get rid of that here. That's pretty much the same. Yep, we're going to serve as well. Actually, let's do it like that. So we're going to create a new AutoCert manager. We tell it to accept the terms and conditions. And we're going to tell it about our host name. Obviously, I'm just going to fake that. I'm not actually going to run it. But let's say you'd own example.com and you would want to quickly generate a certificate for that. You could use it like that. And then we're going to start up our web server like that and tell it to use a separate listener. And that would actually work. That would generate a certificate for you. Using AutoCert. I don't know if you're familiar with that. But that's your entire web server. No config hassle, nothing like that. All right. So that's been an hour and 30 of a quick Go introduction. I hope it was useful to you. You learned a bunch of things. You got a feeling for what Go looks like, what it behaves like. Um, there's a bunch of more things I could probably talk about, like really writing your own little JSON RESTful API. We could go into the tooling, like the linter formatting tools, wet like that. But I think that's probably good for another video too, even. Um, if you're interested, I'd love to do that again. I just after an hour and 30, I definitely need a little break now. I'd love to go into unit testing and benchmarks, which similar to the build system stuff, to the imports that I've showed you, are integrated in the language, which is pretty awesome. The profiling is pretty amazing by now, and I'd love to go get into Delve, which is a Go debugger, and how to use that. But again, that's probably part for another video.